So good morning. As Gustavo said, my talk will be about the evolution of radio sources of jets in extragalactic galaxies and the effect they play on the role they play on the host galaxy, but also the role that the host galaxy can play on them via mass load. I know there are a number of students here, so I will talk about recent work, but I will try to be as pedagogical as possible. Please feel free to interrupt me. And I would also like to make profit to thank Rita for the organization and all the local organizing committee for inviting me and for the organization of the meeting. The outline of the talk is basically a two-part thing. In the first one I will talk about large-scale jet evolution, and in the second one I will talk about the deceleration of jets via mass load by stellar winds. The possibility that the FRII jets, the collimated, decelerated jets, are so just because of the mass load by entrainment of stars within the jet and the interaction with the winds. Well, this is a picture showing 2 kiloparsec scale jets, 3C273 and 3C219, and well, it helps me to tell you that, well, these are two classical FR2 sources in which, I used to have a pointer somewhere. Do you have? Yeah. Forgot it. Okay, thank you. Obrigado. So here you see a collimated jet, same as in 3C273, and strong interaction with the ambient medium on both sides. In this case, we don't see the counterjet in the case of 3C273. That doesn't mean it's not there, but we still didn't detect it. We see only one jet because jets are relativistic, up to kiloparsec scales, and so we have Doppler boosting. In the case of FR2s, in the case of FR1s, you will see some later, they become symmetric because they are decelerated by some process that we have to still to clarify. As I said, jets are relativistic. This is something to keep in mind, but not only kinematically, but also thermodynamically. These plots show they are from the Mojave collaboration, and they show the apparent speed detected in a number of blazars, so jets with small v-wing angles to the line of sight, and you see that they are all superluminal here. This is the minimum apparent jet speed, and here you see that most of them are superluminal. Here you see the numbers go up to tens of C, so apparent velocities that tell you that jets, no matter what they are at kiloparsec scales, they are relativistic at parsec scales. Did I say it properly? No matter what the morphology is at kiloparsec scales, they are relativistic at parsec scales. Well, for students, I will be talking a lot about the jet morphology, and I will be using some nomenclature that I would like to clarify in this and the next slides. Well, this is a basic structure of of a shock generated by a relativistic flow from a relativistic hydrodynamical perspective. If you have magnetic fields, you may have more waves, but in principle, this is what we will be dealing with here today. This is the flow direction, so you have a supersonic jet flow. The red is the velocity, so the jet comes in this direction with a high velocity jet flow with a given pressure and a given density. The jets are very dilute. So what you have is they reach a terminal shock, a reverse shock in the reference frame, in which the pressure jumps, the velocity falls, and the density jumps too. And then there is a contact discontinuity between the shocked jet region and the ambient shocked region, which is here. And this whole region has the same pressure, right? The pressure is continuous, the pressure and the velocity are continuous through the contact discontinuity, not so the density. The density jumps at the forward shock together with the pressure and the velocity for the ambient medium. And after, so beyond the forward shock, which is also known as the bow shock, you have the unshocked ambient medium. So the jet flow is pushing all this structure ahead in such a way that the jet flow has a velocity which is much larger than the shock speed. So this structure moves slower than the flow itself. This is why the relativistic particles in the jet are reaching the jet head. They are shocking because they are supersonic, and then you have these jumps, and you generate a hotspot there. And then what happens with these particles? Well, they fill the lobes. This is a 1D plot, so it's not, you cannot see the lobes here. We'll show them to you in the next slide. And they fill the lobes, and you have radio emission also from these structures. This is one of the first numerical simulations of supersonic jets. I think it was Hughes who produced this plot. Here you have the same plot, but in 2D. You have the terminal shock, contact discontinuity, the bow shock. So what we had in the previous slide was a cut along this axis. So the jet particles that have crossed this terminal shock have nowhere to go but to fill this region here. That's a cocoon, the backflow, right? It's called backflow because it's moving backwards with respect to the jet. Well, you can guess, make an estimate of this shock propagation speed by using the momentum conservation equation and taking into account that across the contact discontinuity, this line here, you have constant pressure. You cross those, and in the end, making some algebra, you reach this equation. I'll tell you about the meaning of the letters now, of the parameters there. In the classical case, you have this, so we can compare them. Here, rho is the rest mass density, h is the jet enthalpy. This is a thermodynamical variable, which is 1 if you use C = 1 units when the jet is cold, when the gas is cold, and it's larger than 1 when the flow is hot. It's relativistic thermodynamically. And here the B means the beam values, A stands for the ambient values, and in the case of relativity, you have also the relativistic case. You have also the Lorentz factor here. We call it, name it with a W. It's a traditional naming in our group. I will warn you when we change it. In some other slide, it will be gamma, right? But I will just tell you. So the difference here lies on you see that here you have the enthalpy and the Lorentz factor, which are not here. The structure of the equation is the same, but of the relation is the same, but you have those new actors that play an important role, as you will see now. Okay. Shocks. This is an FR1. I showed you FR2 before. This is an FR1. Is brighter at the center than on the edges, as opposed to FR2s. And you see that it becomes really symmetric with distance, and from here to here, for instance. And but you also see that, well, you have a flow. It becomes transonic and subsonic at some point because of deceleration, but you still have shock structure here. Here you see the magnetic field, the polarization, and you see how the magnetic field is aligned with this structure. This is telling you that, well, this is probably a shock wave, even if the jet is not supersonic down to the head. This means that all the gas inside this region is overpressured with respect to the gas outside. This is producing and leading the shock waves. So the shock waves are persistent and are relevant in the evolution of these structures. Coming back to classical jets against relativistic jets and the role they play in the host galaxies, I think I will show you now it's important to take into account the relativistic nature of jets. Here we have the expression of a jet power for a classical jet and a relativistic jet. Again, here this is the Lorentz factor, right? So you have, again, the same couple, H Lorentz factor, enthalpy Lorentz factor, and then have density, velocity, and surface here, and jet cross-section. This small gamma is the adiabatic exponent in the case of the classical jet. The rest of parameters are the same. Here's the pressure, density. And if you consider that the jet's velocity is much larger than P over rho in this relation, then you end up with this expression for the jet power. If you consider that the jet is relativistic kinematically and thermodynamically, this means that H Lorentz factor, H gamma, is much larger than C squared, then you get this relation here. Then, at the end of the jet, at the terminal shock, what's the pressure? Well, for the classical jet, in strong shock, you apply Rankine-Hugoniot conditions, and you get this relation. This is the Mach number. In the relativistic jet, you have this expression from using the same expressions, but in the relativistic, for the relativistic case. And you can rewrite this to relate the head pressure with the jet power. In both cases, you can do that. So this is the two relations I end up with in the previous slide. If you equate the powers, you can have a relation, you can obtain derive the relation between the cross-sections in both cases that you need, using the typical parameters that are used, for instance, in simulations of classical jets and relativistic jets. Now I add the subscript C and R for the classical and the relativistic jet. And this tells you that in order to have the same power, using the typical parameters, the cross-section of your classical jet has to be about 100 times larger than the relativistic one. This is because you don't have the enthalpy and the Lorentz factor to help you to accumulate lots of energy flux in a given cross-section, right? Now we come back to the expressions of the pressure, and you end up with this relation between the hotspot pressure for the classical flow, for the classical jet, and the relativistic jet. And you can give the common numbers, and you end up with a hotspot pressure in the classical jet, which is 7% of the equivalent hotspot pressure in the relativistic case. This means that the hotspot pressure you are going to obtain in the case of a relativistic jet is going to be much larger than in the case of a classical jet. We studied this in the context of feedback, of the role that jets play in the environment, because it's common that in that field people are using classical jets. And in the end, the cocoon, the cavity pressure, the pressure of the whole region is going to depend on the pressure at the hotspot, and it's quite different. Okay, this is just to state that the relevance of using relativistic equations for the evolution of jets. Now we go back to the whole evolution of the structure. Again, we have a diagram here for Begelman and Cioffi, 96. You can order of magnitude estimate, or well, the trends using the trends of the evolution of the whole region, using approximations and power laws for the main parameters. And here we have that the estimate, or the approximation that Begelman and Cioffi suggested was that the pressure in this region is, well, it's a dimensional approximation, is the jet power divided by the velocity of the head of the bow shock and the surface of the interaction. Well, this is basically, you can write this as jet power times the time or the age of the source divided by the volume, which is power time divided by volume. This is energy per unit volume, and that's a pressure. So you have also, for a strong shock limit, you have the run pressure equilibrium, which gives you the pressure at the shock. This is the ambient density and the expansion rate. There is a small dot there. I don't know if you can see it. And from these two relations, you can derive a differential equation for the proportionality between the radius of this structure and its the rate of expansion. Solving that and adding some parameters, we extended this model, allowing the flow to have changes in the head velocity and the ambient medium to have a slope, a decreasing behavior, and then we got some power laws. And interestingly, if you develop this in the adiabatic case, so no strong radiative losses for the cocoon and the whole structure, you end up with a relation for the cocoon temperature, which is of course P over rho, and P over rho are evolving in the same way, so you get that the temperature in the cocoon should be constant. The problem is to measure the temperature of a region that only emits non-thermally. But if you could measure it somehow, you could relate the temperature in the cocoon to intrinsic parameters of the source, like the jet power and the mass flux, which is here. Okay, because, well, taking into account that you can measure the cross-section of the region from the observations, and if you have an estimate of the jet power, you could even make a guess on the flux. Well, this is all the analytical part. I'm moving now into simulations, and I will come back to the comparison with these analytical models to show you that they work, to give an extent, they work well. This is the equations we're solving. I will show you in the first part of my talk, I will show you purely RHD simulations, 3D evolution of jet, long-term evolution of jets in galactic environments, homogeneous fall of pressure and density outside the galaxy. And in the second part of the talk, I will add the magnetic field for study of the evolution of jets that are mass loaded by stars. Here you have the main equations, mass conservation, momentum conservation, energy conservation, and then the Maxwell equations that are added. In yellow, you have the magnetic terms. And relevant points that you have to take into account here is that, well, the pressure you have, from the pressure you derive this beta demagnetization, which is magnetic to internal gas energy density ratio, and from the modified enthalpy you have sigma, which is the magnetic to rest mass energy density ratio, which tells you about the role of the magnetic field in the dynamics of the flow. Well, the relativistic and magnetic effects come when beta is larger than 1, sigma is larger than 1, and also when, in the case of the purely hydro-relativistic case, when, as I said before, h, which is here, is larger than 1, and when the Lorentz factor is also larger than 1. The simulations I will show in this first part were set up initially for 2D simulations, for the case of axisymmetric simulations. I will show some of those too. This is the profile for the ambient density. So we're injecting the jet at 1 kiloparsec from the formation and following its evolution. This is a profile that comes from a radio galaxy, 3C31 from Hardcastle et al. 2002. And so it comes from a real radio galaxy. Not too much changed by the evolution of the jet, because that's an FRII. And we used different jet powers, started with a jet radius of 100 parsecs, and in the 2D simulations, we injected the jet during that given time and then switched it off to follow the evolution after switch off and check whether the bubbles that are used to explain feedback from AGN in the environment were being formed, and the shock was disappearing. I will show you that we didn't find that in these cases. The simulations were running in the active phase between 16 and 50 million years, and we switched off around 200 million years. So the passive phase was pretty long. A warning note, this is work by Wagner and Bignell in Sydney. And they show that the evolution of jets in simulations is very different if you include a cloudy inhomogeneous medium and if you don't, right? As I told you before, in our simulations, we're using a homogeneous medium. This is the first kiloparsec, right? So this is where you expect to have a cloudy and strongly inhomogeneous medium. So our simulations start here, when the jet has crossed this region and actually is developing in a more homogeneous medium. In the 2D case. In the 3D case, we added some changes in the ambient medium, not as dense and as clumpy as in this case, however. Okay, so this is to be taken into account, right? So if you are going out the galaxy, maybe this is a good approximation. Inside the galaxy, you need to take this into account. So as you see, these jets resemble quite more this one. This is, by the way, I forgot to tell you that in our code we use also the Singe equation of state, so we are using leptonic jets, and in some cases we introduced an electron-proton jet in this case, but mainly inject leptonic jets in the simulations, and the ambient medium is ionized hydrogen. So this is the low power jet after 50 million years. Here you have, this is 200 kiloparsecs, and this is a high power jet up to 500 kiloparsecs. See, the morphology is completely different. The deposition of energy occurs in different scales, time scales, and and spatial scales. And once you switch off, this is what they produce. In order to maintain in the galaxy in hydrostatic equilibrium, we had to include a gravity term in the equations. And in the case of the low power jet, after many million years, the flow is kind of coming back, and if you see the cuts, I am not showing them here, but the profiles of the density of the galaxy are recovering, are coming back to the initial state. The bow shock is very, very weak. And in the case of the high power jet, you have, sorry, this is stress mass density and this is temperature. So here you have a really hot and dilute cavity generated by the injection of the jet, surrounded by the shocked ambient medium, with still mild shock surrounding it. Yeah, the size here now, this is 200 kiloparsecs, so this is about a bit less than 400, and in this case here, this is 900 kiloparsecs. Thank you. This is the final snapshot for the high power jet. You see again temperature density, hot and dilute structure, which could develop into a bubble, a floating bubble, but this is still, this whole region is still driven by the pressure difference between the whole shocked structure and the ambient medium, and thus the motion is not buoyant. It's driven by the shock still. How efficient is this process in terms of energy deposition in the ambient medium? In these plots, I show, for the same jets I showed you before, the total injected energy until the moment we switch off here. This is the solid black line. And then the red lines stand for the energy accumulated by the ambient medium. And these lines stand for the energy that is kept by the injected particles. And this is the potential energy gained, because you are moving material outwards. So you see that, well, the dotted lines are internal energy, the dashed lines are kinetic energy. So you see that the internal energy gained by the ambient medium is very, very close to the, this is a logarithmic scale, sorry, this is energy, this is not 60 ergs, this is 10 to the 60, sorry, this is log energy. And in the end you see that, well, 90% I'd say of the injected energy can go into the ambient medium, and this is due to the shock heating. I come back to the relation between classical and relativistic jets. This is the expression I showed you before, and this is the maximum pressure that the cavity can have. This is, as I said, power times divided by the volume. These two cases are relativistic, and this case is the classical one. So you see that here we're showing the pressure in the cavity related to the maximum one. You see that in the case of the relativistic jets, it's about the pressure in the cavity is about 40% of the maximum one, and constant. This tells you that it's the pressure in the cavity is proportional to the maximum one. Whereas in the classical jet is much smaller in the beginning. It rises with time, and this is because this is the volume in the different models. And you see that the volume occupied by this jet is smaller, and therefore, as you are injecting the same amount of energy, the pressure is rising, right? So if we go to the efficiency, relativistic, classical, we see again that for relativistic jet, the ambient medium is getting almost all of the injected energy, whereas in the case of the classical jet, you have a pretty different relation. The lines are more close by, mainly in the beginning, which is where you can compare using analytical solutions. When the 2D effects come into play and you have the volumes playing a role, if the volume is smaller, you will have an increase in pressure, of course. So this is when you can compare them better. And here you see that the distribution of energies is completely different. Now we have jumped into 3D simulations. I'm showing here the jet velocity. Here you have the color scale. And here you have a cutoff close to the jet head for the positive velocities, and these are negative velocities. This is backflow. It reaches like -5. The jet is extremely collimated. This is an FR2 jet. We injected also some perturbation at the jet base in order to make it wiggle and obtain the 3D effects of jet evolution, so dentist drill and so on. And we follow this along 200 kiloparsecs. 3D simulations are more expensive than 2D, you know. This is the rest mass density. Again, you see the well-collimated structure, the backflow, the cocoon, extremely elongated. If you see here, I can show you the hotspot produced by the jet. This is the pressure in colors, and then with a limit, and then in the lines show you the tracer, which is the jet mass fraction. So this is the contours that give you where the jet material is, more or less. And this is a surface, an isosurface for different values of this jet mass fraction. You see the jet well collimated, and here you see that the shocked gas is moving backwards. We knew all this from previous simulations. However, we're doing it for a decreasing density ambient medium and introducing a galactic profile from a real galaxy. And this structure actually reminds me of jets like 3C273 or 3C219 or Picture A that was shown yesterday by Professor Blanford. And why is that? Why are they so collimated, and what's happening with these jets? Here I'm showing the jet position with time for, these are different 2D simulations, and this is our 3D simulation. You see that the 3D jet is faster than the 2D jets. This is the opposite from what you would expect from the dentist drill model, because in the dentist drill, when the 3D instabilities start to develop, you would have the momentum would be spread in a wider surface, and then the jet evolution gets tired and it's slower. It's not the case. The 2D jets are attached to the axis and they are evolving slower in the same ambient medium. Why? Well, it happens that this small perturbation that we introduced at the jet base has to develop to nonlinear amplitudes in order to develop the dentist drill. However, as it grows, and it doesn't grow very fast because the resolution is low, you know that the growth of instabilities depends on the resolution. If you want to make them grow as they should, you need very, very high resolution. We know this from development of Kelvin-Helmholtz instabilities in laboratory simulations, so to say, that I did in my thesis. Until that moment, the amplitude of the perturbations is very small. What this does is it tilts your front shock with respect to the ambient medium. So there is an angle. And if the front shock is a planar shock, the deceleration is very strong. However, if the shock is tilted, the deceleration is not so large. And then this favors the acceleration of the jet down the pressure and density gradient, and you end up with a 3D evolution which is faster for a time than the 2D ones. When time goes by, this is only 2 million years, after 5 million years you can realize that the 3D simulation is slowing down. Here is when the dentist drill is taking care of or is playing a role in the evolution. But by that time, the 3D jet is at 200 kiloparsec while the 2D one is at 60 or 70. So it makes a difference. And this is maybe why you see in sources like 3C273, you see small wigglings of the jet, but you see it's still extremely collimated, and it's only one-sided, which tells you that it's relativistic down to the interaction side. Here I show the evolution of the 3D simulation is the solid line, the 2D simulation is the dashed line. You see they are very similar. Here we have pressure of the cocoon. The cocoon is the backflow region, density in the same region, the volume, and the temperature. These are all logarithmic, and this is linear. You see that, as I said before, the simulations are reproducing that the temperature in the shock region is basically constant, as expected from the analytical models. And here you see that the pressure in the 3D case is a bit smaller, gets smaller with time, but this is because you are occupying a larger volume because the expansion is faster too. So the pressure drops faster. And the same happens with density. If we go to the models, here I only want you to pay attention to this is the same model I showed you before. These two lines here for this is 2D jet and this is the 3D jet. And you see the evolution of the pressure here, for instance, and you see that the numbers are pretty similar from the simulation and from the model in all the cases. So this tells you that the model works well, but why is it working well? But it's working well because the pressure inside the shocked region is proportional to the maximum pressure. And this was the hypothesis. But this is because the jet is relativistic. Otherwise, you see, the proportionality is lost, and then the model wouldn't work in that case. It wouldn't work so well. What happens with efficiency? This is the 3D case, this is the 2D case, again, with some differences for the jet, but we see that the energy deposition in the ambient medium is really efficient, and jet shock heating can be playing a very important role in this feedback process. In powerful sources, of course. I showed you the 2D simulation that I showed you before. The shock is milder. The efficiency is high while the shock is active, but while the source is active, but when it switches off, then the thing changes quite a bit because the amount of energy that you put into the system is smaller. Here I have a comparison of some relevant parameters of our 3D simulation with real sources derived from the literature. So I chose sources that were morphologically similar to ours and that had similar powers, estimated powers. And well, you see that the numbers that we are getting are basically in the order of magnitude of what you see, but for the time, for the ages. The ages are slightly smaller in our case. This is because the ages that we get from the literature are obtained basically from synchrotron aging and radiative cooling. And in our case, well, we know the age because we have the simulation data. And our jet is evolving very fast because of this tilt. But regarding the other parameters, now I continue with the pressure inside the lobe, the volume of the lobe. It's also smaller. This is maybe because it's extremely collimated in our case, also because it's younger. And the velocity is slightly larger too than the ones in observations. Mach number is similar. Here you have the references of the papers from which we got the numbers. But in general terms, we get order of magnitude values, very well comparable, well within the observational estimates. So the conclusions from this part is that the shocks can be the most important heating mechanism in powerful radio sources. And this can happen in a really efficient way and fast. 90%, as I said, of the injected energy can go into ambient medium mainly via shock heating. And 3D simulations are confirming this point. I move into the second part of my talk, mass load by stellar winds. Here you have some images, X-ray images of Centaurus A, and you see that there are some knots here that are suspicious and could be maybe interactions between the jet and clumps of gas or stars that are just orbiting around the center, and at some point they get into the jet. If we come back to the FRI paradigm by Bignell, suggested by Bignell in the 80s, we see that the suggestion was that deceleration takes place from the shear layer from the boundaries of the jet to the jet axis in a kind of gradual process. There are a number of other models taking over and developing this idea by Wang et al. And here there is a model by Leng and Bridle for sources like 3C31, FR1 jets that model the observed structures and derive well-defined velocity evolution of the jet using the asymmetry or symmetry of jet and counterjet and the magnetic field structure, as I'll show you. And well, I would like to mention that there is a recent paper by Komisarov and a student of his, I don't recall his name, sorry, and which they suggest the growth of an instability on the boundary layer of a jet that is expanding and recollimating to explain this deceleration. However, this model suggests or assumes that there is a single recollimation shock. So a recollimation shock would be like these structures here. between the jet origin and the place where the jet is decelerating. And from parsec scale images, we know, VLBI jets, we know that there may be more than one recollimation shocks in between those regions. However, it's a very interesting idea. It's just a new kind of instability to explain small-scale entrainment and turbulence and getting into the jet axis. It's published in Nature Astronomy last year. So here is the modeling that Lang and Bridle produced for some FR1s, well-known FR1s, and this is the velocity with distance, and you see that the drop, this is basically speed of light, 0, that the change in the velocity of the jet is kind of gradual. It's not discontinuous, but in one case. It's a kind of weird case, but the others kind of are changing gradually. And here you see the transverse structure of jet velocity. At some point you see that jets are decelerating and developing wide shear layers, right? So are expanding and decelerating. Together with that modeling, they showed that the regions that I showed in the previous slide are coincident. This is deceleration region. This is the one that was just a discontinuous decelerated jet. But the others have an extended deceleration region, and it coincides with high emissivity in the X-rays. So it's a dissipative process. You are in training material and dissipating kinetic energy in producing X-rays. So one of the processes that could lead to this result could be jet and star cloud interactions. Was suggested as a scenario for knots in M87. Now we know that in that case, those knots in the boundary of the jet, correct me if I'm wrong, but those are basically the jet ambient interaction in the shear layer. But later on, the Komisarov took over the idea of the interaction between jets and stars, for instance, and he showed that this problem can be treated as a hydrodynamical problem. So the scales in which the interaction and the mixing between the jet and the tail formed by the stellar wind are large enough to consider this as a fluid problem. Then Bowman, Leahy, and Komisarov developed stationary steady-state solutions for mass-loaded jets and showed that actually these jets, very low power though, could be decelerated by mass entrainment. In addition, this scenario has been claimed to be the source, possible source, for high energy radiation by a number of authors. And it's an interesting way to add protons into the jet and accelerate them, or a number of them. We produced some 2D and 3D simulations of jet cloud star interactions, and well, here you have this is an inhomogeneous cloud. You have a core here, so time goes like this, and you see how the structure is widening as it heats up by the shock wave that is crossing it, and in the end you end up with the hard core, with the very dense core. But all the boundary of this inhomogeneous cloud has been built. This is an axisymmetric simulation. In this case, this is a 3D simulation of a star surrounded by a shocked stellar wind entering in the jet. Here the jet is going in this direction, and the star is orbiting around let's say the stellar, the active nucleus, moving into the jet. Here you see that there is a wave propagating upwards, upstream, and this is because here there is a shear layer, there is a transition in velocity, and there you generate a wave that is moving upstream, and we had to stop the simulation here because we were changing the injection conditions. But this is a 3D plot with some carbon lines. In the turbulent region you cannot trust them so much, but you can see how the jet here is deviated from its direction. So this direction is that direction. You are seeing, this is the 3D image is seen from here, and you see that you are generating a tail, lots of turbulence, and that this 3D instabilities developing in the tail are growing fast enough that actually the mixing takes place in small scales, in small scales in relative terms to the jet size, right? This simulation is meant to represent the interaction at 100 parsecs from the jet, and the size of the region is only a fraction of a parsec. This is 6 times 10 to the 17, so it's half a parsec. Right. What we get from these simulations, this is again from the 2D, is that this is the jet energy before the interaction and after the interaction, normalized to 1. And this is the internal energy in the jet, internal energy in the wind material, and you see that the kinetic energy in the jet, which is dominating at the injection, is kind of going down and being invested into internal energy, that the cloud gas velocity rises in reasonable distances. Here, this the 2D experiment, the 2D simulation was made closer to was meant to represent the interaction much closer to the black hole. The mass flux in the jet is increasing in almost 1 order of magnitude. This is at half the grid, and this is an estimate of the radiative output of PP processes as seen at 20 megaparsecs. And these are the limits, observing limits for Fermi and very high energy detectors. So this shows, together with this work by the work by Sarka-Wikes, that part of the very high energy output from relativistic jets could be generated by jet-star interactions. You can have flares if there is a strong interaction between one big star and the jet, and you can have, as in this case, the sum up of all the interactions can give you kind of a background X-ray emission for the jets. This is, well, Sarka-Wikes estimated that there can be up to 800 million stars of different sizes inside the jet in Centaurus A. To me, this number is huge, but I don't know, this is the number she got. So, and depending on the fraction of young stars, the young stars are more powerful and have stronger winds, you can have more flux at the high energies or less. So the first simulations we did in this respect were the 2D simulations, dynamical, coming back to Bowman et al. Steady state, steady solutions. We produced simulations with the same parameters, but injecting a jet into a decreasing density ambient medium and from a dynamical point of view. Here you have, well, this is a funny structure that is generated. Again, the scales of this evolves. The jetware had just such a small power that the evolution was taking place in time scales that were smaller than the dynamical time scale of the gravitational field. So in the end, you ended up with a hot spherical region at the jet base. However, going back to the jet, well, this is the profile of the part ambient medium, and this is the profile for the stellar population in the grid. So the stellar population for us is a source term in the mass equation, and you have a number of stars in each cell. So this gives you a mass load source term. And we were using stellar mass losses typical from low mass stars in red and dead galaxies, in ellipticals, as they were. Here I show the axial velocity. You see that there is, this is the injection velocity, 0.95, and this goes down to 0.2 here. And this is the leptonic mass fraction. Here we were injecting our jets as leptonic jets, and of course the stellar winds are proton-electron, and you see how, from the very beginning, you're changing the composition of the jet. You can see this better in these plots. For simulations without mass load or with small mass load rate, the jet velocity is basically constant. This is in centimeters per second, down to the interaction with the ambient medium or disruption by the growth of instabilities. However, in contrast, if you have a relatively important mass load, the velocity goes down continuously. Here, the scales at which this deceleration takes place are well recovered by this relation derived by Hubbard and Blackman, in which they kind of account for the distance at which the jet cannot drag anymore all these particles. So using momentum conservation, using the momentum conservation equation. Here you have the size of the jet, of the head of the distance at which the head of the jet is with time for the different models. This is more powerful jets, they don't care, they go straight. And less powerful jets, these two with little or no mass load and with strong mass load. You see that this is converging to a stagnation point, and this could maybe be a way to produce jets that are kind of compact. They don't grow into large distances like FR0 ones, FR0 jets, which were suggested by Baldi et al. Some time ago. Now I move into the RMHD regime, and here what we're doing is to produce steady state solutions a la Bowman et al., but introducing magnetic fields into the equations. We are using an approach developed by Komisarov et al., in which you assume that the jet axial speed is close to the speed of light. You have to assume this in the equations to produce this kind of setup, and that the radial field is basically zero, no radial or toroidal velocities for the jet. And by doing this, what you get is a setup in which the axial coordinate, z coordinate, can be taken as time. So you are solving the transversal equilibrium along z, along time, and you produce solutions. This is a comparison between a dynamical simulation and this simulation. So you see that the approximation for an oscillating jet is quite good. This is a complicated setup. We have top hat profiles. This means constant values inside and then constant value outside with a discontinuity for density, axial velocity, axial field. And we have this structure for the toroidal field. It comes from numerical simulations by Lind et al. In 1989. It gives you a, an axial current along the axis and return current along the jet boundary. And we solve the transversal equilibrium equation. This is all set up in such a way that, again, we have ambient pressure falling with distance, only one dimension, right? So only z. And stellar mass load distribution that also changes with distance. So in order to account for the change of the stellar number density with distance to the nucleus. And we pretend to, study the deceleration of sources like these ones. And for that, we're using mass loads which are slightly larger than the ones I showed in the 2D dynamical simulations, but this is like 10 to the minus 9 solar masses per year accounts for stellar distribution with a large number of red giants. 10 to the minus 11 is closer to kind of low mass load in elliptical dead galaxies. The jet composition is leptonic, the stellar wind again electron proton, and here you have the jet power. Here this is the contribution of the Poynting flux, and here you have kinetic plus internal energy. So the H has the 1 plus specific internal energy terms. The 1 will give you kinetic energy. The internal energy is going to give you the internal energy flux. Here, I'm not going to tell you much about this, only that here are all the simulations we did. These are 1D simulations. They are cheap. And here you have the distribution for all of them, kinetic, internal, and Poynting flux energies. And the results are given in images like this, which you have the pressure with distance, Lorentz factor, plus poloidal streamlines. You cannot see them here. Magnetic field, axial field. You have all the relevant physical parameters in maps like that. And now what we do is to produce, we make cuts and we obtain mean profiles for the jets. And what we get here, I will show you only 2 examples. This is a dilute jet, very, very dilute. This is like 10 to the minus 8 times 1 proton mass per cubic centimeter, and mild mass load. So we're taking kind of low mass stars. So here we see that, well, the injection Lorentz factor is 10, but as we are taking, there is a small shear layer, all the mean values and cylindrical coordinates, the shear layer weights more because you weight all this with the volumes, and then the Lorentz factor is decreased, but the Lorentz factor on the axis is 10. Okay, we see that for different pitch angles, these are colors stand for pitch angles or no magnetic field, we have, well, similar behaviors. In this case, we have the jet temperature drops because of the injection of the protons. The jet density rises orders of magnitude because of the injection of the protons. And the Lorentz factor kind of, yeah, decreases, but then tends to a constant value. And this is the jet radius from 1 parsec at injection. It's growing, but it's growing less in the magnetized jets than in the non-magnetized jet. And this is just because of the magnetic hoop by the toroidal field. If we go to denser jets, this is 4 orders of magnitude more in density, we see that the Lorentz factor also decreases, tending also to basically a constant value. And in the case of the density and temperature, we see some funny behaviors were already pointed out by Bowman et al. And we see that there is an increase in temperature in the magnetized jets and an increase in density at the same time. This means that the kinetic energy, these jets have more kinetic energy because they are more massive at the injection. They are dissipating kinetic energy into heat because of the interaction with the stars. So they are heating up, and then they are evolving, they are expanding because of this heat up. And then they can kind of accelerate and counteract on the mass load. So the effect of the mass load would be to decelerate, but the jet expansion is, by the Bernoulli process, is giving acceleration when you have internal energy to put into the kinetic energy. So there is a constant transfer between energy fluxes when you have the scenario to produce them, when you have the energies. Here we have the energy fluxes. Here's the total energy flux in a jet. Here is the kinetic, internal, and Poynting flux. And you see that in this case, this is constant. There is no change. However, the magnetic flux here is dropping. And this is, these are the plots that are showing this is the black line or a red line because they are the same here. And you see when there is strong mass load, this is a strongly mass-loaded jet, the jet radius is changing in a non-linear way. Let's say it's not conical expansion. And this is giving you a conversion of magnetic flux into kinetic flux and helping you, together with the internal energy, to, it's not acceleration because you see that the Lorentz factor is dropping with distance, but it's delaying the deceleration of the jet with respect to the non-magnetized flow that decelerates very fast. And this is due to the help of the magnetic field that avoids very fast expansion. If you expand very fast, you introduce lots of stars inside the jet and you decelerate faster. And also it's giving you this acceleration. This is another example. We have the same. Magnetized jets are decelerated in longer distances, like 200 parsecs, than in the case of the non-magnetized jet. The increase of density is huge, but again, we have non-conical behavior of the jet radius and this of the expansion, and this is giving you possibly this differential expansion that you need to account for magnetic acceleration. I will end up with this diagram, Softlocks diagram, to explain. By the way, one warning note: you cannot believe our results from beyond Lorentz factor 2 because the approximation, as I said, is meant for very fast jets. So this diagram explains everything we got from these simulations. If the ambient pressure drops, the jet radius grows, and then if the mass load is larger than a critical value that you can derive from the mass flux conservation, then the density grows and the Lorentz factor drops. If the Lorentz factor gets to 1, this is the end. You decelerated your jet. If it's different from 1, then you can use the momentum flux conservation to get 2 different behaviors. If the enthalpy is larger than 1, sorry, if this relation is not true, this means that the enthalpy will grow because there will be investment of kinetic energy into internal energy, your enthalpy will grow, and this will favor further expansion. If this relation is true, this means that your jet will doesn't have enough kinetic energy to convert into internal energy, so what it does is it cools down, and you end up with questioning yourself whether your enthalpy is different from 1 or is equal to 1. If it's different from 1, this is the end of this branch. You cannot ask more questions here, but you can go to another branch and keep asking questions about the magnetic flux conservation and what the magnetic acceleration can do for you. Do I have a minute to explain that? Or yeah, thank you. This other branch, for instance, if the mass load is not larger than the critical value, you will have expansion, and then you will have, due to adiabatic expansion, you will have a decrease in the rest mass density, and then depending on your enthalpies, if your enthalpy is larger than 1, you will have Bernoulli effect and acceleration. If it's 1, this is the end of this branch, and we can continue here because I will come back here later. So you will have expansion, drop in density, drop in internal energy, and acceleration. If you don't have magnetic field, this branch is not telling you anything, you have to go to these branches. If you have magnetic field, you can have a magnetic acceleration. Do you have it? Yes, then magnetic field drops, and then this is invested into acceleration, so you increase your Lorentz factor. If you don't have magnetic acceleration because your expansion is purely conical, then via magnetic flux conservation, your magnetic field still falls, and then depending on the relation between the toroidal field and the kinetic flux, you can have further expansion, and here you connect again to this branch because an increase in the Lorentz factor is giving you a drop in the relative weight of the magnetic flux. And well, I leave you with the conclusions here, and that's about it. Thank you very much for your attention.